I'm still not used to that. Okay, there we go. Whoopsies. Instantaneous velocity of an object at time t is defined to be the limit of the average velocity of the object over shorter and shorter time intervals containing t. Now I'm going to do a illustration of this on the next page to try to make a bit more sense what I mean by the limit of the average velocity. But essentially what this is trying to get at is you want to take average velocity over an interval that's so obnoxiously close to the number you care about that it essentially gets rid of all ambiguity. You're using 2 points that are so close to each other that it's going to be able to give you a decent approximation of essentially the velocity at that singular point that you're caring about. Now, just like with average rate of change and average velocity, there's the velocity statement of this kind of idea, and then there's the general statement of this idea. So we have instantaneous velocity, but in general, it's called the instantaneous rate of change. So just like with average rate of change is essentially the same thing as average velocity just has context. Same idea here. Instantaneous velocity is the same thing as instantaneous rate of change, just that velocity is in a specific context. So the instantaneous rate of change of f at a, so at a certain point a, which is also called the rate of change. Sometimes they drop the word instantaneous and just say find the rate of change, is defined to be the limit of the average rate of change of f over shorter and shorter intervals around a. So essentially that same idea of average velocity, just now in a more generic situation here. And again, I'm going to illustrate this in just a second to try to make it make a bit more sense. So essentially, what we're going to be doing is we want to find the average rate of change for as small an interval as we can. Officially, if you really want to, scare your friends with some scary looking math notation, officially, this would be defined to be the limit of this thing, and I'll try to explain this in a second as well. Now, don't panic, because this looks like something you already know. This is essentially an average rate of change, this thing I just wrote here. It's just got an x plus h in there instead of a b and an x instead of an a. And what this is essentially saying is we're taking the average rate of change between 2 points. So this would be the point that I care about. And then this x plus h would essentially be super close. And essentially what this limit is doing is saying, essentially let that h value go to 0. Get as obnoxiously close as you can without actually being that same point. You don't have to worry about this official notation. Like you don't have to memorize it or anything, but that's kind of what's going on here. And if we did talk about limits a bit more, we would be using this, but we kind of just have this idea of taking the average rate of change for as small of an interval as we can. So, can we do some freaking examples? Yes, we can. First thing though, so I'll leave this up for like 5 more seconds in case someone's still getting it down. I want to draw the picture first, and then we'll do some examples. So, picture first. So if you're following along, it's actually at the bottom of the next page. Now, I haven't defined this yet, but it's the same idea as what we're talking about now, so I'm going to just skip down here and draw it now. So say I have some function, and I want to know, let's say this is 2, this is 3, this is 1. Sure. Say I want to know about the instantaneous rate of change at 2. So essentially, I would want to know kind of the slope at 2. Why did I say slope? Let me go here. So let's go back to the idea of that last example we were looking at. We had, essentially, we found the slope between, I'm getting ahead of myself. Let me stop and backtrack. Here we are. Say I eventually want to work up to the instantaneous rate of change at 2. How do I do that? Because I only know how to calculate average rates of change. Well, I could calculate the average rate of change between 1 and 3. The slope of this line would be the average rate of change between 1 and 3. So remember, the average rate of change is a slope. So it's going to be the slope of that line between 1 and 3. But what if I start getting closer to 2, which is the thing that I said I actually care about? Let me take 2 points that are closer to 2. Let me find the slope of that line. Well, the slope of this line is the average rate of change between, let's say that's 1.5 and 2.5. And if I keep essentially getting closer and closer points to 2, one on the left and one on the right, if I keep getting closer and closer points to 2, that approximation, that average rate of change is going to get closer and closer to the thing that I actually want. Because here's the thing that I actually want. Green. What I actually want would be the slope of this line here. And let me write the words in black because that green's a little bright. The slope of this line here would be the instantaneous rate of change. Instantaneous. But the reason we can't immediately calculate the instantaneous rate of change fully is because that green line, I know they're all kind of mushing together, but that green line only touches the function at x equals 2. It doesn't cross through more than one point. It only touches that function at x equals 2. So how do I find the slope of a line if I don't know another point that's on that line? Which is why we have to use this idea of using 2 points. And you can either use 2 points that are both close to 2, or you can use 2 and a point close to it. But since we need to use 2 points to find the slope of a line, we need to use the point that we care about and a point obnoxiously close to it. And that's going to get us as best of approximation as we can to the slope of this line that literally only touches the graph in that one point. Hopefully that makes sense. I feel like I can explain this a lot better when y'all can see me pointing at things and waving my arms around. But so essentially we want the slope of this line that only touches the graph at that singular point. But since we need 2 points to find the slope, we need to essentially take the best we can, which is the point we want, and a point obnoxiously close to it. So what does that look like when we actually do it algebraically? So leave this up for another 5 seconds. And then we'll scroll back up. So say I have this first example here. The quantity in milligrams of a drug in the blood at time t is given by that function right there. Estimate the rate of change, which again is equivalent to the instantaneous rate of change. They sometimes drop the word instantaneous, of the quantity at time t, and interpret your answer. So essentially what we want to do is we're going to take the average rate of change between 3 and a number very close to 3. So let's say I personally essentially always use the point that you're caring about, and I always just tack on a 0, 0, 1 to it. If you would like, there's a kind of a few other options you can do. You could just take 0.01. I would not suggest going any, so this should be essentially the lowest you go. Maybe I shouldn't say lowest. So not 3.1 is what I'm trying to say. So essentially, when I say obnoxiously close, I mean obnoxiously close. So 3.1 is actually slightly farther away than we want to take it to be. So essentially, the closer you get, the better. So 3.01, 3.001 are kind of the two best options here. Or you can also go in the opposite direction. So this would technically be moving 0.01 to the right. You could also go backwards if you want. So you could also do 2.999 or 2.99. And again, I would stop there. 2.9 is a little too far, if you will. But those are kind of your options. And usually I just default to 0.001, tacked on to the end of whatever the heck I care about. Now, depending on what you use, you can get a slightly different answer. And when I say slightly, I mean slightly. So just be aware of that. If you use 3.001 and someone else uses 2.999, you're going to get the tiniest difference in your answers. When it comes to Wiley, let me make a note on Wiley for next week. There's some notation for this. Usually they'll say something like, why is my pen not working? Come on. Like let H equal 0.001, which means that the difference between the points that you're looking at has to be 0.001, which would be what we have right here. So they'll sometimes tell you what they want the difference between the two numbers to be. Sometimes they'll say this, sometimes they'll, make it instead 0.01. Is there another way they do that? I think it's usually H. You might see change in X, just in case, but I think they usually phrase it as H, to kind of tell you the difference that they want, if they're trying to, make sure you get the right answer that they want, if that makes any sense. So anyway, how the heck are we doing this problem? We're taking the average rate of change for 3 and 3.001. So we want the average rate of change for 3 and 3.001, because we need the slope of a line, and we can only do that with 2 points. So since we want the slope at 3, we have to take the slope between 3 and something really close. So now we're essentially going to plug 3. Well, I usually like to take the larger value first. So we're going to plug the 2 into the function to get our y values essentially, and then divide by our x values. So we've got our function here. Scrolled over a little bit too far. So we have our function we were given, 25, 0.8 to the t. So if we plug in 3.001, oh, I actually have the wrong thing in my notes, so I have to calculate this. I have to calculate it off the bat. 25, 0.8 to the 3.001. It's going to be 12.797. Let's round it to 3 decimal places. Actually, let's take a few more. More decimal places is always better to start. And then 25 times 0.8 to the 3 is 12.8. So we have negative 0.002856 divided by 0.001. I ran out of space to interpret. Divided by 0.001. It's going to be negative 2.856. Now these are, Q values over T values. So our units here would have been milligrams per minute. And like I said, I ran out of room to interpret. Let's just squeeze a little bit in here. Interpret. So say I want to interpret this. Well, first off, are there questions on how I found that? Yeah. Let me. So we have our function given was 25 0.8 to the t. And so this one was 25 0.8 to the 3. And I just plugged those into my calculator. Yep. Okay, so say I don't see any more questions. Say I want to interpret this. Now I'm going to scroll down really quick and then I'm going to scroll back up. So don't worry, it'll come back up in a second. The average rates of change were slopes. The instantaneous rate of change is a slope. So if I want to interpret this, I'm going to interpret this like a slope, which we did way back when. I told you it was going to come back to slap us in the face. Here we are. So remember also there was essentially two options for writing your interpretation of the slope. There was essentially the rate way and the kind of increase by 1 way. I'm going to go ahead and use the rate way this time. So what we would say is we would say after 3 minutes. The reason for that is we kind of always have to tell them where we're starting. So since we're talking about t equals 3, we should tell them after 3 minutes. So after 3 minutes, the quantity of the drug in the body, so the context, is decreasing because it's negative at my slope value, milligrams per minute. So we can always interpret slopes in terms of just the slope value as a rate, and to say that essentially the y value context, so in this case it was the quantity of the drug, so after 3 minutes the quantity of the drug is decreasing by that slope value. Questions, concerns on that? Okie dokie. So it seems like I'm moving on to a new definition and not going over another example of this, but we're actually defining an equivalent thing. So we have, I'm running out of space a little bit. I'm doing really bad with my spacing today. The derivative of f at a, really fancy f for functions. So the derivative of f at a, which is written like this, and we would call this, the way you would read this is f prime of a. So the derivative is defined to be the instantaneous rate of change. So the instantaneous rate of change and the derivative are the same thing. So we've essentially just defined another way to say instantaneous rate of change. And introduced this new notation to be able to kind of no longer have to say the words instantaneous rate of change. We can just say f prime of whatever we want to care about. Sorry? Maybe that was an accident. Okay. So say I want to do an example of this, which again is an example of an instantaneous rate of change also. So say I want to estimate f prime of 2 if f of x is x cubed. So what we want is the instantaneous rate of change at x equals 2. Well, how do we find the instantaneous rate of change? So from that, we want an average rate of change at x equals 2 and something obnoxiously close to x equals 2. So again, I personally like to just tack a 0.001 at the end. Let me just list a couple of the other options. Well, maybe the other main option is to go the other way and to just use 1.999 instead of 2.001. But that's essentially, again, this is what we have to use to calculate the instantaneous rate of change. We have to estimate it using the average rate of change. Now I only choose one of these. I don't do both of them. Well, I guess I could if I wanted to get a better approximation, but I'm just going to use 2.001 personally. So we would essentially want the average rate of change between 2.001 and 2. So I'm going to plug 2.001 and 2 into x cubed. So let me kind of do that down here. So if x equals 2.001, f of 2.001 is going to be 2.001 cubed. So 2.001 cubed, 001 cubed is, now also I should say, when you're doing these, take as many decimal points as you can, because it'll make your answer not only better, but also in terms of Wiley, it'll help. If you round too early, it'll really mess up a ton of things. So this is, I'm going to say 8.012, you know what, 006 even. I'm going to take a bunch. And then I'm going to subtract f of 2, which would be 2 cubed, which would be 8. 2.001 minus 2 would be 0.001. So we have this guy. Which would give us 12.006. Now, some of you who might know derivatives, if you already know derivative rules, you know that the actual answer would be 12. So if I had just rounded a bit earlier, I would have got the actual answer, but I specifically avoided that because we are estimating here. And for giggles, not that I really have the space for it, but I'm going to do it anyway. Say you wanted to use the other value, 1.009, just to kind of show that we can use. Did I miss a 0? Yeah, no, I just missed a 0 when I was writing it down. I think, so did I mess up I think I typed it into my calculator right though. Yeah, I typed it in my calculator right, I just wrote it down wrong. Sorry about that. So say we wanted to go the other way. What you would get from this would be, not negative because I switched it around. Yeah, no, sorry. I didn't mean to confuse you. I just dropped a 0. So this would give you approximately 11.994. So that's what I mean by you'll get slightly different answers depending on kind of which value you use, but they're both obnoxiously close to 12. Like, it's not that one's more right than the other one. They're both decent approximations of what we care about. If you have an issue with Wiley, let me know. I don't think it's very bad for 2.1. They usually have a decent enough tolerance, and it's not a notation thing. It's just a tolerance thing, unlike with 1.5, where the notation was the thing that was the issue. And also make sure to read their instructions. So they might tell you, again, what they want you to take as kind of that extra value if they want you to tack on a 001, or they just want you to tack on, say, just 01. Excuse me. So try to make sure you read their instructions, take as many decimal places as you can to start with, and then go back to their instructions and double check that you round to where they want you to for your answer as well. But anyway, Questions, concerns about calculating the instantaneous rate of change, which is equivalent to estimating the derivative. Okay. All right. So average they're not the same thing, average rate of change and instantaneous rate of change. The unfortunate thing is, so instantaneous is estimated using average rate of change. So we calculate the instantaneous rate of change by using an average rate of change, but it's because that's the best we have right now. Eventually, again, we're kind of building up to the actual formal thing that people use in calculus. So right now, we actually aren't calculating exactly the instantaneous rate of change. We don't know how to do that yet. So what we do know how to do is we can estimate it by using average rates of change. So that's why we're using the average rate of change process, because we're using the average rate of change to estimate the instantaneous rate of change. But technically, they're slightly different things. The instantaneous rate of change is essentially going to be the slope at a singular point, which might not make sense to say, but that's what it is. It's the slope at a singular point. Whereas the average rate of change is essentially the slope of a line between 2 points. So there's like this slight nuance of a difference between the two. I'm over here in my office waving my arms at myself. But anyway, there's a slight nuance between the two, but we use the average to estimate the instantaneous, which is why they kind of seem similar at the moment. So though I want to stress again, so we're finding slopes. That's technically what we're doing here. So always in the back of your mind, remind yourself that the average rate of change and the instantaneous rate of change is a slope. Specifically because of the thing I'm about to do right now. So let's go down here. It's possible we'll finish these notes today. That's impressive. All right, so we've got the graph of x squared right here. And I want to determine if the following are positive, negative, or most likely 0. So essentially, we're given these derivative values. Now remember, the derivative we just found out is equivalent to the instantaneous rate of change. And the instantaneous rate of change is a slope. So if I want to look at, I'm going to bring out all the colors. So let's look at f prime of 1. What I'm going to want to do is I'm going to want to go to f of 1, which is right here. And essentially, if I were to draw a line using the same slope of 1 and a point obnoxiously close to 1, I would pretty much get a line that looks like this. Hopefully that makes sense. Like if I take 1 and take the point 1.001 and drew the line between them, it would pretty much look like that, right? Is the slope of that line positive, negative, or approximately 0? In class, I'd usually wait for an answer, but I'm talking to a screen, so the slope of that line is positive, which would mean that f prime of 1, I don't know what it is. Well, I do, but we don't know what it is. We haven't calculated it, but it's going to be positive because this line has a positive slope. Well, what about negative 1? Let me go over to negative 1. And let me draw a line that essentially follows the function at that point. You know, if I were to pick a point really, really close to negative 1, what would the line look like? Well, is the slope of that line positive, negative, or 0? That one's got a negative slope. So I don't know what the actual value is, but I know that f prime of 1 is going to be negative. Purple. What about f prime of 2? If I go up to 2, f of 2, I go over to 2 and then up to the function. And say I take a point obnoxiously close to that and draw the line between the two of them. Maybe I should have been doing that this whole time, marking another little point on there and drawing the line between the two of them. We didn't actually calculate it. So we're not calculating the slopes here. It's just if you look at this line, the blue one, I don't know what the slope is, but I know it's going to be negative. So we're not actually looking for the actual values here. We're just trying to see if it would be positive, negative, or possibly 0. So I don't know what that actual slope value is, but I know since that function is, since that line, that blue line is decreasing, that it would be negative. So now we got this purple line going on. Well, is that going to be positive, negative, or 0 for the slope? Again, don't know what it is, but that's an increasing line, so it's going to be a positive slope. And then, let's see. Oh, pink. That's different enough. There we go. So then if we look at 0, if I'm at 0, I pick something obnoxiously close to 0, I'm essentially going to get a line that's just straight across, really. So looking at that pink line, what's the slope of that pink line? Well, I don't really, well, this one we kind of do know what it is. That's going to be 0 because it turns out to be a completely horizontal line. So we can say we actually know the value there. If it's a horizontal line, the slope is 0. So we're going to say it's approximately 0. We're not entirely sure it's 0, but it's looking like it's going to be a horizontal line. So we're going to guess that it's probably approximately 0. Does that make sense? So we aren't finding values here. We were just using the idea that the instantaneous rate of change, which is the derivative, is the slope of a line. So if I drew those lines, we were just looking to see if that line looks positive, negative, or 0 slope-wise. Questions, concerns on that? Alrighty. So let's do the same kind of thing, but the tiniest bit different. Down here. So we've got the graph of f of x, and we want to indicate whether the following are positive, negative, or approximately 0, and we're going to illustrate them. So the first thing I want to talk about is f prime of 1. Well, again, that's going to be the slope of a line. So we go up to the function at x equals 1, and we essentially, pick a point that's obnoxiously close to it. And I draw the line between them. Well, is the slope of that line positive, negative, or approximately 0? We'll have positive there. If I want this thing here, f of 3 minus f of 1 over 3 minus 1. Now to illustrate this, we kind of want to think about what that's actually representing on the graph. What does that look like? Hopefully that looks like a slope or an average rate of change. Both of those would be acceptable answers. So that looks like an average rate of change, which is a slope between 3 and 1. So essentially what that's going to show me on the graph is the slope between these 2 points. Let me draw the line between those 2 points. Well, that's turning out to be a horizontal line. So we can say that this is probably at least approximately 0. We don't know exactly what it is, but it looks like it's probably going to turn out to be approximately 0. Since this looks like a slope. So it looks like, well, it looks like a slope because it is a slope. That looks like our slope format. Y2 minus y1 over x2 minus x1. Now this last one is a bit different. So, well, here's f of 4, and here's f of 2. How did you graph that last one? Yeah. So look at this. F of 3 minus f of 1 all over 3 minus 1. That looks like this, just with 3's and 1's. So this is an average rate of change form. But remember that the average rate of change is a slope. So essentially, since it has this format, I can think of this graphically as the slope between 3 and 1. So I went over to x equals 1, went up to the function, went over to x equals 3, went up to the function, got those 2 points, drew the line between them, and the slope of that line between them is exactly what would be represented by this. Does that make sense, Julia? I think it's Julia. Your name's cut off slightly. That makes sense? Well, yes and no. It had to do with recognizing that that looks like a slope. But it wasn't like it wasn't that I looked at this immediately and went, oh yeah, I just draw this line. I kind of had to do some thinking of, that looks like an average rate of change. But the average rate of change is a slope. Okay, so this would be the slope between 3 and 1. Well, what does that actually look like? That would be the slope of the line between the 2 points. So let me go draw the line between those 2 points. So this last one, I got a minute. So those are our 2 points. So technically, on the graph here, this one's a bit weirder. This kind of distance right here would be our value. But we do have to think a little further, because is it going to be positive or negative? Well, f of 4 is smaller, and f of 2 is the larger value. So while it represents this distance, since we're taking a smaller value minus a larger value, it's going to turn out to be negative. And my pen isn't working suddenly. So you might not immediately see negative because you just see this distance here. But then you just have to think about which one of these two was larger than the other. F of 2 is actually larger. So a smaller number minus a larger number is, of course, a negative number. I'm out of time. We'll do the last one on Monday. Not exactly, Kayla. So if you need to leave, feel free. If you've still got questions, stick around. So specifically because, how do I explain it? We were illustrating what the actual numbers would look like, and maybe I should have been slightly careful, and I probably should have said, the slope of this line is technically what we're looking at, and the slope of this line is technically what the number is. But with this one, this calculation is not representing a slope. It's just calculating subtract two numbers from each other. Now we can represent that graphically as essentially the distance between the change in y between the two of them, but it's not actually a slope. So we don't want to draw a line because that's saying that we're looking at a slope when we don't actually have a slope here. Does that make any sense? So it's like a completely different graphical representation. It's not actually calculating a slope, it's just taking those two y values and subtracting each other. So we just kind of end up with what is represented as this kind of distance between the two y value y's. That was a bad way to put that. But essentially, no, because we don't have a slope, we have just a subtraction of two things. Anybody else got any questions? Okay, yeah, so we're looking at f of 4 and f of 2. So that's essentially the y values. So the y value at 4 is lower than the y value at 2. Like, I agree that 4 is larger than 2, but comparing the y values, the y value at 2 is larger than the y value at 4. You're welcome.